Hi students, how are you? I think it's fine. And I think all of you checked my previous video. That means the first lecture of periodic table. So myself, Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering, welcome you all in my second lecture of periodic table. You know, in previous class we discussed about the history about the periodic table. That means that how there was an effort to develop the proper arrangement of the atoms or elements. So one by one scientists came to the field, starting from Devonier to Newland to Mendeleev, then the properties of the modern periodic table, etc., etc. Today we will discuss about the few factors, like first of all we will discuss the properties of the each and every block. Previous class I told you that there are 4 blocks S, P, D and F. So today I will give you some information about the each and every block. That means there are some peculiar properties of the each and every block. Today we will discuss about that particular properties of that block. Then we will discuss about the different kinds of atomic radii, like it's a van der Waals radii, metallic radii, and then obviously we will discuss about the ionic radii. Okay. So first of all we will discuss about the properties of the each and every block. So in the previous class I told you that if we look the periodic table, it can be classified in the 4 blocks. Okay, so first block, that is the S block, in the left side of the periodic table. In the second block, that is the P block, in the right side of the periodic table. Then it is the middle position, there will be D block, and the bottom position there will be A block. Okay, so generally these all are the metals. Here is the mixture of mainly non-metals, but some metals are also available here, and some metalloids are also available. Here is the transition elements, and these are called the inner transition elements. Okay, so this is the general classification of the each and every block, or general properties of the each and every block. So first of all we'll discuss about that what are the characteristics of the S block elements. Okay, general characteristics. If we consider the general characteristics of the S block, then first of all the S block elements are highly reactive. If you think about the sodium is highly reactive. Even you can't keep the sodium in open air. So that all the elements are very much reactive if you consider the S block elements. If you think about the S block elements, they are good reducing agent. What is the meaning of reducing agent? Reducing agent means they can be easily reduces. They can be easily oxidized, and they can easily reduce the other elements. Self-oxidized means a loss of electrons. So if you think about sodium, so sodium easily it can lose 1 electron, and then it can be self-oxidizing, so that means it can reduce other very first. Okay, so that's why it is called their highly or good reducing agent. And third one, as they are generally the metals exist in the S block elements, in the category of the S block elements. So they are good conductor of heat and the electricity. So this is the expected. Okay, so generally all the elements have a very high electricity carrying capacity and as well as the heat carrying capacity. And third, that is the very important, you have to keep in mind the general electronic configuration of the S block elements. The general electronic configuration is that if you first one is the NS1 and second one is the NS2. That's why here it is written NS1 to 2. This is the general configuration. Okay, that means all the elements exist in the S block that are in the category of either 1 to 2. So this is the general classification. And another thing, what I told you, that they can easily lose the electrons. So obviously they have the tendency to form the ionic compounds. If you take the simple example of sodium form almost ionic compounds NaCl, Na plus and Cl minus. So almost they have a tendency to form the ionic compounds. Okay, so these are the general properties of the S block elements. Another case is that the p block elements has the higher ionization energy. What is the ionization energy? I will discuss. Okay, that is included in your syllabus. So I will discuss in the next class that what is the ionization energy. Then you will understand that p block elements has the higher ionization energy with respect to the s block elements. Okay, so then the most important point here that the p block elements, all the elements have the maximum elements have the variable oxidation states. That means they can show different oxidation states in different compounds. Okay, so starting from the phosphorus, all of you know very well that phosphorus has the different examples of regarding different oxidation number. Okay, so that type of variable oxidation states can be possible for another elements of the p block elements. Okay, so now another important thing is that you have to keep in mind that the general outermost electronic configuration. Okay, so NH2 NP1 to 6, that means all the elements the common oxidation or common the electronic configuration is that NH2, but their variable valence electron changed in case of NP subcell. Okay, in maybe 1 2 3, not 1 2 3 4 5, maybe anything. Okay, so that will vary from 1 to 6. So that general electronic configuration also you have to keep in mind for each and every block. That will be very important. Okay, so for S block that will be NS1 to 2, and for P block that will be NH2 NP1 to 6. Okay, so now we'll move to the general characteristics for the D block elements. Okay, so if we consider the characteristics of the D block elements, then the most important point for D block elements are is the all the elements here, all the elements are metals. Okay, so they are generally transition elements in between S and P block, and they that the elements act or the block act like a acts like a bridge in between S and P block. That's why that block is called actually transition. Transition means transition in between S and P block. So that all the elements here, that all the elements are generally metals. Second point is that in case of 5D elements, actually in case of 5D elements, there are some elements like platinum, Au, Hg, etc. They generally inert. Inert means they generally do not react. Okay, so in general condition. So that's why they are called noble metals. Okay, so these elements are called noble metals. Now generally that all the metals are solid, but all of you know very well that there exists one metal which is not solid. That's why that is called the mercury. So mercury exists in the D block, and mercury is not the solid, it is in the liquid state, all of you know. So except that mercury, all the elements are very hard and all the elements are solid, and they form that all the elements form either ionic or covalent compound, and they also show the variable oxidation numbers. Okay, so another thing is that transition elements, they form that the elements form generally colored complex compound. Okay, or coordination complexes. Okay, so complexes means the metal can form several bonds with the ligand or the ligand, and the compounds are very stable. That compounds are called actually complex compound or coordination compounds. Okay, so generally that transition elements participate in the formation of the coordination compounds. Okay, that is the main important another important point or another important properties of the transition elements, because depending on that fact there is another chemistry that is called coordination chemistry. Okay, totally different depending on the different concept or different phenomena. So that's why that is also very much important point. Okay, and like other previous cases also, you have to keep in mind that the general electronic configuration for the d block elements, that is the n-1 d 1 to 10. I will show you that the electronic configuration that but according to above principle, which we already discussed in the previous class, last class of the atomic structure, you know, I think that that the d starting from the 3d, like 3d come at first, then it will be 4s. Okay, that means that should be, but actually what happened, 3d come first, then it is the 4s. Okay, so that should be, but actually what happened, that 4s it filled at first because its energy is lower. Okay, that 4 plus 0, according to the above principle, 4 plus 0 is 4, but in case of 3d it's 3 plus 2 is 5. So expected 4s will be filled up at first. So that's why look here 4s vary only 1 to 2. Okay, but the outer electron, or 1 by 1 electron, when you move from left to right, the electron come to the n-1d. It may be 3d, maybe 4d, like that. Okay, so the d electrons will be filled up 1 by 1, and that's why here at first n-1d, because if it is 4s, like it will be 3d, like that. Okay, and here why 1 to 2? Actually there are two cases may be possible, either before half filled or before full filled of the d orbitals. Then one electron from the s that will jump to the d orbital. Why? Because the half filled or full filled d orbitals are very much stable. That's why here it may be 1 or 2. Okay, so this is the general electronic configuration of the d block elements. Okay, now come to the f block elements. Okay, f block elements are called, actually there are two types of f block elements. First one is the lanthanides. Okay, first row is called actually lanthanides, and the second row, that is called actually actinides. Okay, lanthanides and the actinides. So first of all, look here that all the elements are heavy metals. Okay, so all the f block elements are heavy metals, and also that elements have the variable valency. Like d block elements also have the variable valency, but in compared to the d block elements, f block elements have very much higher variable valency. Different types of valencies are available for the f block elements. Okay, like that elements have high density, very high density, high melting points and boiling points, and also it is the general electronic configuration for the f block elements. Like, you know, f will come again before that d. When we'll move to the higher elements, then the electronic configuration become n-2f 1 to 14, n-1 d 0 to 1, and n is 2. So that is the general configuration of the f block elements, which you have to keep in mind, because that is also important when we'll discuss today. Also we'll discuss about the lanthanide construction. Then you have to actually that electronic configuration is very much important to explain regarding the explain the reason of the lanthanide construction. Okay, so now these general properties you have to keep in mind, that S block, P block, D block, and A block. Okay, and now we'll move to the atomic radii. Okay, now come to the point that how we can determine the atomic radius or atomic radii. Actually, the atom is taken as the sphere. Okay, so if we take the atoms that are sphere, that the atoms are the sphere, that means obviously the size of the atoms that should be expressed by the radius. Okay, but there are some problems in determining the radius of the atoms. Okay, what are the problems? The first problem is that isolation is not possible. Okay, if we want to isolate the a particular atom, a single atom, is it possible to isolate a single atom? It is not possible. So that's why the direct measurement is not possible. Okay, second thing, that we have to think about a sphere. That means there should be some boundary, but if we think carefully that the electrons, that if it is a nucleus, so we are taking it, it looks like a sphere, but actually the electrons are not restricted to a particular boundary. Okay, if there is no particular boundary, then again there is a problem. There is a problem regarding the determination of the atomic radii. And the third very important point, that atomic radii or atomic radius that also changes from one bond to another bond, from one bond to another bond. That means there are some factors which act on the atoms, that's why the attraction force or the electronegativity or different kinds of factors, depending on these factors, that atomic radius also not fixed. That means if it is possible to isolate a single atom without interference of any other atom or like that, then it is possible that atomic radius will be fixed. But exactly, or not the theoretical condition, in experimental or in practical condition, it is not possible that atom will be without the interference of any other atoms or bonds or like that. So that's why there must be interference. If there is interference, then obviously there will be some changes. Okay, so due to that difficulties, actually there different kinds of concepts are there, or different kinds of atomic radius which we have to measure, either not directly, that indirect method, or due to some calculation, by the calculation or like that. Okay, so first of all, there are three types of atomic radius are possible, or we consider, so depending on the different situations. Okay, so first one is the covalent radius, second one is the metallic radius, and third one is the van der Waals radius. Okay, so if we consider the covalent radius, that's simple, that if two atoms, they are covalently attached, suppose there are two atoms, okay, they are covalently attached with each other, then what happened? Then the distance between the two nuclei, if it is the distance between the two nuclei and the distance is a, if we take it is a, then covalent radius will be a by 2. Okay, so covalent radius will be a by 2. That means what I am telling, that it's simple, that if the two atoms, they are attached with a single bond or double bond or whatever, by any covalent bond, then what happens? There is an expectation that the distance between the two nuclei, if it is a, then obviously the covalent value for one atom, that will be a by 2. That means if it is R a, then obviously R a plus R a. Okay, that means it's each and every atoms has the distance between the two nuclei, it will be a, R a. So that indicates that if it will be 2a, then it will be 2a. Okay, so it will be 2a, then it will be 2a by 2, or it will be a. So that means if that distance will be a, so R a equals to R a divided by 2. Actually we are taking RAA means 2a, so it is the 2a by 2 generally. But this application will be only possible for homoatomic molecules. That means the two atoms are A and A. If the two atoms are not A and A, that means if here there is two atoms, like one is A and another is B, first one is the A and second one is the B, then the distance between its distance and its distance will not be same, may not be same. Then what we have to take? Then we have to take R A B, that equals to R A plus R B, isn't it? So that means R A, any of the atoms covalent radii equals to R A B minus R B. So that will be the equation for the covalent radius for any of the molecules. Okay, so now come to it is the covalent radius. Now the metallic radius, actually in case of metals, generally it is taken as that the distance between the half of the distance with the corresponding or the side atoms. Okay, like in case of if we take the copper, atoms, then the distance between the two copper atoms is the 2.6 angstrom. Okay, the distance between the two side by side or copper atoms or neighbor copper atoms, then obviously the metallic radius will be, it is for copper, It is for copper. Metallic radius will be 2.6 by 2, then whatever 1.8 something. So that will be the 2.6 actually 2.6 angstrom. 2.6 actually angstrom. Then it will be that 1.8 angstrom will be here. Okay. So now, if we consider that van der Waals radii, that is another type of radii. Metallic, in case of metallic radii, in metals you know that there is not such kind of any proper or prominent bond like covalent or like that. There are different kinds of bonds or different kinds of theory available for metallic bonds. That's why there different kinds of concept is also applicable for the metallic radii. Okay, and we are taking half of the distance between the two adjacent atoms. Okay, so by that method we are calculating the metallic radius. Okay, now in case of van der Waals radii means it is the distance between two neighboring atoms. Okay, half of the distance between two neighboring atoms which are attached with a covalent bond with another atoms. Okay, that means if you see the picture, then it will be more clear. For example, this is the Cl2 molecule. Okay, Cl plus Cl. There are two chlorine atoms are attached by the covalent bond. Okay, this is the Cl2 molecules, and here it is the another Cl2 molecules. Okay, so what is the van der Waals radii? According to the van der Waals radii, the half of the distance means, for example, if we consider that two atoms, then if this is the distance between the nucleus of two atoms, then half of the distance, that means that distance, half of the distance of the two atoms which are attached with the covalent bonds with other atoms. Okay, that means that two atoms are attached with the covalent bonds with other atoms. So that distance is called, it is the van der Waals radii. Okay, so this is called the van der Waals radius. Okay, so that is this is another type of actually radius which is not directly acting in a particular bond where the atoms are attached with a particular covalent bond, but that is also important because you know that van der Waals force is very much important for chemistry or for the molecules also, so which we have to consider each and every case. So van der Waals radii also important, radius also important very much because that are acting with the non-bonded molecules. Okay, look, there is no direct bonding between the two molecules, just there are neighbor molecules. Okay, so with that neighbor molecules, then half of the distance between the two molecules, is obviously here all the cases the distance between the nucleus, as we are taking the atoms are sphere and in the center there are nucleus, so obviously here distance indicate the distance between the nucleus. Okay, so now the distance between the two nucleus of the two atoms which are non-bonded, but it is bonded with the another atom. Okay, so that effective distance is called actually van der Waals radii. Now there may be some order, that what is the order of the three radius, that is the covalent radii, van der Waals radii and the metallic radii. So obviously the order will be, if we write down R, it is the covalent radii, first one, it is the highest radii, highest means no, it is the distance will be lower here, then R it will be the metallic radii and R van der Waals radii. Okay, so van der Waals radii will be more higher with respect to the metallic radii. I think this is very much clear from the picture also, because look, there are no bonding connection, so obviously that distance will be higher, so that's why van der Waals radii will be higher here, the distance will be higher, so that's why it is higher. And then metallic radii, it is a middle in between the van der Waals radii and the covalent radii, and the last one will be the covalent radii. So that was in the covalent radii, because covalent radii means they are directly connected with each other, so expected there will be the shortest distance in comparison to the other atomic radii. Now come to the point that how atomic radii change, or the atomic radii is changing with if we move from the left to right side of the periodic table or top to bottom of the periodic table. That means if we move according to the periodic table or from the point of view of periodic table, what change we can observe for the atomic radii. So for that purpose, first of all, you have to understand one thing, that what factors are mainly responsible either increasing the atomic radii or decreasing the atomic radii. That is the nuclear charge. Okay, that is the nuclear charge. Okay, so if it is a nuclear charge is responsible for the decreasing or increasing the atomic radii, then what happened according to the period and what happened according to the group? Try to understand. According to the period, what happened? It is a group. According to the period, what happened? Look here. According to the period, if we move from boron, carbon, nitrogen, oxygen, fluorine. This is the common period which we are taking as an example. So if we take that example, then just consider the electronic configuration. Okay, just consider here the electronic configuration for boron. Here electronic configuration, it will be the outermost electronic configuration will be 2s2 2p1. For this case, for carbon will be 2s2 2p2, nitrogen 2s2 same, 2p3, oxygen 2p4, and fluorine 2p5, and so on. Okay, that is neon 2p6. Okay, so now if we move from left to right, then what change we can observe? The change is that what changing we can observe here. The change is that one by one electrons are entering in the same quantum number. That means no extra cell is added. Okay, just try to understand carefully. Here, from here, it is the 2p. So one by one electron come and join in the 2p if we move from left to right. But nuclear charge, that is the number of protons which is mainly responsible for the nuclear charge. So number of protons in the nucleus, that increasing when one electron is added here, again one proton is also added in the nucleus. That is, if we move from boron to carbon, just try to understand, if we move from boron to carbon, one electron is added nucleus, one proton is added in the nucleus, but one electron is added in the same subcell. Okay, 2p, no same subcell, no extra cell is added when we move from boron to carbon, but nuclear charge, that is increased. So if there is no sufficient addition of the cell, but nuclear charge that is increasing from one step to another step, then obviously what happened? The attraction force will be increased from left to right, isn't it? Attraction force will be increased from left to right when we move from left to right. Okay, so if attraction force increases, then obviously size will be decreased. Size will be decreased. So what is the conclusion? Conclusion is that from left to right, when we move, one proton is added in the nucleus, nuclear charge is increased, but electron that is added in the same cell, okay, or same subcell, whatever. So that means the nuclear attraction force is increasing one by one step, but no extra cell is added when we move from left to right. If attraction force is increasing, then obviously size will be decreased from left to right. Okay. Now if you come to the across the top to bottom, okay, that means according to the group, then what change you can observe? So from top to bottom, here you can, if we write down that boron group, boron, aluminium, gallium, etc., gallium, thallium, etc., there are the so many elements are present here. So just write down here, I'm writing here that the electronic outermost electronic configuration 2s2, here 2p1, here 3s2, 3p1, here 4s2, 4p1. So what is the change in the outermost shell? The quantum number is increased. That means the principal quantum number is increased. That means 2, 2, 3, 2, 4. So if quantum number is increased, then that indicate that extra cell is added from top to bottom. If extra cell is added from top to bottom, that means with nuclear attraction the extra cell is added. But if extra cell is added for the nucleus, it is not possible to attract with the same energy or the same force like the previous cell. So that means the size will be increased, isn't it? So when extra cell is added, that means nuclear force or nuclear attraction force is not sufficient, because extra cell is added with addition, or if we come from the top to bottom, if we move from the top to bottom, then nuclear force, attraction force will not be sufficient to attract the outermost cell. So that's why the size will be decreased here. Okay, so what is the conclusion? According to the period, the size will be decreased, and according to the group, it will be increased. Okay, so when we move from top to bottom, the size will be increased at the attraction force by the nucleus that are decreasing. If attraction force decreasing due to addition of extra cell from one element to another element, so obviously size will be increased. So this is the conclusion of the atomic radii, that according to the period it will be decreased, according to the group it will be increased. So now we'll discuss about the electronic configuration. I think many of you, if you know the electronic configuration, that's good. If you don't know, then check here that either how we can give the electrons for each and every individual subcells from the cell. That means from the previous class, you know that the K, L, M, N. So that are the corresponding orbits are there, and for each and every orbit there are some subcells also there. Like for K, it is the 1s, here 2s, 2p present, and here 3s, 3p, 3d, and here 4s, 4p, and 4d. And already I discussed in the previous class that what will be the order of the energy order, that is how electron will can take place in each and every subcells. Then it is according to the above principle. Okay, so if it is according to the above principle, you can check my previous video where we discussed about the above principle. So then what is the final configuration? The final configuration, it will be starting from the 1s, then 2s, then it is the 3s, then 3p, then 4s, then 3d, and so on. Okay, we have to follow. Okay, here it will be 2p. Okay, so 1s, 2s, 2p, then 3s, then 3p, then 4s, then 3d. Okay, so that order we have to follow, and according to that order, we have to keep in mind the atomic number. Okay, so like if we consider the boron, so first of all you have to know what is the atomic number of the boron. So for that purpose, you can keep in mind that starting from the hydrogen, that hydrogen 1, then helium 2, then hydrogen, helium, lithium 3, then beryllium 4, then boron. Okay, so boron will be 5. So in that way you can keep in mind, because you have to keep in mind some elements, sequence of the elements, like starting from the hydrogen to neon, that you have to keep in mind. Hydrogen to neon, that you have to keep in mind for the exam purpose. And groups you have to keep in mind, like the groups of the S block and the P block elements mainly you have to keep in mind, because each and every valence electronic configuration. What is the valence electronic configuration? Okay, I will show you that what is the valence electronic configuration, then I will tell you. Okay, so then starting from the 1s, so you know the maximum capacity of the maximum electron carrying capacity of the 1s, that is the 2. That all the things we discussed in the atomic structure chapter. Okay, if there is any doubt, then you can go to the just atomic structure class, then that factors will be more clear to you. Okay, so 1s2, then it will be 2s2, again 2s maximum capacity is the 2, so obviously it will be 2s2, then 1s2, 2s2, so 2 to 4. Okay, so there are 1 electron remaining, so it will be 2p1. So if it is a 2p1, so that means the valence electronic configuration means what is the valence electronic configuration? The valence electronic configuration means you have to consider the highest number of principal quantum number. Okay, so 2 is the here highest number of principal quantum number. So how many substances are included with the highest number of your principal quantum number? That is called the valence electronic configuration, and that you have to keep in mind, because different kinds of properties of the elements which we can explain with the help of the outermost electronic configuration or the valence electronic configuration. Okay, so that's why this is very much important here. Now if we take another example, like if you take the example of fluorine. Okay, so now what is the electronic configuration? Like boron 5, then after boron it's carbon 6, then boron carbon nitrogen, then 7, oxygen 8, then fluorine 9. Okay, so it will be 9. Now if you give the electrons, okay, one by one, then what happened? 1s it will be 2, then 2s it will be 2, then 2p, how many remaining electrons? 2 to 4, remaining electron 5, so 2p 5. So 2s2 2p 5, it is the outermost electronic configuration of the fluorine. Okay, so that you have to keep in mind, 2s2 2p 5, it is the valence electronic configuration. Now I told you that you have to keep in mind at least the groups of the S and the P block elements. So why you have to keep in mind, I will show you. Like if we consider any of the group, like it is the group of boron. Okay, so boron, aluminium, gallium, etc, etc. Okay, gallium, indium, thallium. Okay, so like indium, like thallium. Okay, so now the electronic configuration of boron, which we already discussed about the electronic configuration of boron, that is a 2s2 2p1. So that means all the elements of that group will be electronic configuration NH2 NP1, NH2 NP1. All the elements should have the same electronic configuration like NH2 NP1. Okay, so that means if it is 2, here it will be 3, here 4, here 5, and here it will be 6h2 6p1. So how beautiful thing is that? Look here, that if you know the electronic configuration of boron, you can write down the electronic configuration of thallium. You can write down the electronic configuration of gallium, isn't it? So that means valence electronic configuration is only important things which you have to keep in mind, but it is not possible in the exam time to keep in mind that what is the outermost for any question purpose. If it is required, that what is the electronic configuration of indium. So it is not possible. Even if you keep in mind the atomic number of indium, it is not very much easier work to write down that one by one electronic configuration to reach the last electronic configuration. That is very difficult job in the exam time actually. Okay, so that's why better if you keep in mind the groups of each and every groups, then it will be more helpful for the exam purpose. Okay, now I will show you the another electronic configuration for transition element. For example, scandium. Okay, so scandium, its atomic number 21. Okay, then just write down the electronic configuration of the scandium. Then it will start from 1s2, 2s2. It will be 2p6, then 3h2, then 3p6, then what are the remaining electrons? 2 to 4, 4, 4, 4 plus 6, 10, 10 to 12, 18. Okay, then after that it will be 4s2, because you know that after 3p it will be 4s, then remaining 1 electron will be 3d1. Okay, so because in case of transition elements, 4s come at first, which we already discussed in the above principle, that 4s will be filled up at first, then D. So here it will be 4s at first, then 4s2, then 3d1. Okay, so that is the process. This is the process of the electronic configuration which you have to keep in mind, because each and every case electronic configuration for the elements are very much important in chemistry. Okay, so without electronic configuration we can't move. It is not possible to move actually in the chemistry. So that's why just keep in mind how you can identify the valence electrons majorly, because valence electrons are the main important thing for each and every element to identify its different kinds of properties. Ionic radii we can define in this way, that the influence of the nucleus on its electron cloud, up to which the electron cloud exists. Now the problem is that there is no particular boundary of the electron cloud. So that's very much difficult, that how much the attraction force of the nucleus will be for its electron cloud. So that's why generally the ionic radii determined not in the direct process. It is determined in the indirect process. So for example, if we take it is the NaCl, that means it is the Na plus and it is the Cl minus, it is the Cl minus, then what happens generally, we will take the ionic radii means its the distance between the up to that point to that point. So this is the cationic radii. So up to that point it is the cationic radius, and up to this, that means here it is the cationic radius and here it is the anionic radius. Okay, so in this way there are so many methods actually, like Pauli method is the very common method by which we can determine. There are some equations also. From that equations we can determine the ionic radii, but this is not in that all the methods are indirect method. Okay, there is no direct method by which we can determine the ionic radii, because there are so many factors are included here. Okay, so in case of ionic radii, first of all, if we consider that how ionic radii will change, or if we want to compare the ionic radii of the two ions, then first of all we have to know commonly that if Na, that is the any of the atom, when it loses one electron it forms Na plus. So generally what happened, that radius of the Na, obviously that will be greater with respect to radius of the Na plus. Why? Because here look, the number of protons and number of electrons, if there is x number of protons attract y exactly x number of electrons. Okay, because Na is the neutral, so if it is neutral atom, obviously x number of protons will attract the x number of electrons, isn't it? But in the second case, look here x number of proton attract x minus 1 number of electrons. Okay, so this is the main thing behind the that ionic radius will be always lower in case of cations with respect to its neutral atom, because if here number of proton attract the same number of electrons, but here number of proton attract the electrons, if it is a single positive charge, then one less number of, or one lower number of the electrons. That means if it is the 5 electrons attract the 4 number of electrons. If it is 10, then 10 number of proton attract the 9 number of electrons. So the attraction force will be more stronger. So if attraction force will be more stronger, that means its size will be lower, because if it is nucleus and if that lies at the subcells, okay, then what happened? The nucleus attracts the subcells, or nucleus attracts the orbitals or orbits or whatever. Okay, so then what happened? If the nucleus is increased, then what happened? That orbits or the subcells will be attracted more. Okay, and that depends on the number of protons. So number of protons and number of electrons ratio actually determine the what will be the there is also another factor that is called screening effect. I will discuss later what is the screening effect. But for this case, just try to understand that only number of protons versus number of electrons. So number of electron lower here, that means attraction force will be higher, so size will be lower. Okay, its opposite case will be in case of anion. Okay, so if you consider any of the anion like Cl, So if you consider Cl, when Cl take one electron, it will be Cl minus. Okay. So now if you consider the size radius of the Cl and the radius of the Cl minus, obviously Cl minus has the higher radius with respect to Cl. Why? Same reason. Here number of proton and electron same, but here number of electron is higher. Number of electrons are higher with respect to the number of protons. So in the second case, look here, the lower number of protons attract higher number of electrons. So attraction force will not be stronger like the previous case. So obviously its size, if the attraction force will lower, then obviously its size will be higher. So in case of anion, size increases from with respect to its neutral atom, but in case of cation, the size will be higher size will be lower with respect to its neutral atom. Now come to the point that what will be the order of that means the increasing or decreasing order of the ionic radii, either from group or according to the table or period of the periodic table. So first of all, look here that you have to know that if we take the cations of different charge for the same atom like Fe, Fe2 plus and Fe3 plus. So I think all of you understand very clearly that why Fe2 plus has the higher size with respect to Fe3 plus. Same concept. Here number of protons attract the electrons. How many electrons will be attracted by the protons here? Here one electron is lower with respect to there. So same number of protons, if n number of protons attract here y number of electrons, here n number of protons attract y minus 1 number of electrons. So same number of protons but electron number is lower, that's why attraction will be higher. If attraction will be higher, size will be lower. Same case but in opposite direction for anions. If anions charge will be higher, if anionic charge will be higher, its size will be higher because here proton have to attract more electrons with respect to the its lower charge anions. Okay, so that means that two things are in opposite direction. You have to keep in mind for exam purpose because that kind of question you may expect. Okay, so here if for cations with increasing the charge, its size will be lower. For anions with increasing its charge, the size will be higher. So if we consider the group trend of the cations, then obviously it is almost same with the trend of the atomic radius. Like according to the group, the atomic radius was also increased. So here, look here, that in the same order that is followed by the ions also. That means either cationic radius or the anionic radius. If we move from the top to bottom, then the size of the cations or anions that will be increased. But in case of periodic trend, that means when we are considering the anionic or cationic size for the according to the period, then we have to keep in mind the comparison should be according to the isoelectron. Okay, so the comparison should be the which have the same electrons, same number of electrons. Okay, so if we consider for the periodic trend, then we have to keep in mind the ions should be isoelectronic. That means the sodium, magnesium and the aluminium, it is according to the period, and that three cases the charge, that means sodium plus, Mg2 plus, here it will be Mg2 plus and Al3 plus. So that three cases, look here that the number of electrons are same. Okay, so if number of electrons are same, obviously number of protons are also in that three cases, number of protons are higher in case of aluminium with respect to sodium. So what happened, because from left to right atomic number is increased, so that's why here proton number is higher but the electron number same with respect to all the three cases. Okay, here proton number is lower, here proton number is higher. So obviously if proton number is higher, So obviously if proton number is higher, then obviously it attracts more strongly the outermost electrons. So that's why if it attracts the outermost electrons more strongly, then there is a chance of the decreasing the radius. So that's why here the trend is the according to the following way we can explain. In case of anions, look here that nitrogen, oxygen and fluorine. Here also if we follow nitrogen, oxygen and fluorine, almost same order with respect to the atomic radius, because here in case of nitrogen 3 negative, oxygen 2 minus, and here if 1 minus, that also same number of electrons present. But look here number of protons is lower, here number of protons that is higher. So that's why here number of protons attract the more number of electrons with respect to here number of protons higher but electrons same. So that's why here attraction force will be more higher as the electron number of protons are higher. So here attraction force will be more, and but here in this case here attraction force will be lower. So that's why here the size of the N3 minus, that is the higher size. Okay, that's all for today. Now we'll discuss the next topic in the next class. Okay, so before that, just prepare all the topics which we discussed today. Goodbye, take care.